So I gave you a food for thought yesterday, where the idea was to go ahead and prove that the greedy algorithm that we designed for finding this minimum spanning tree using the Prim's algorithm is a situation where the algorithm will always generate the minimum spanning tree. Okay, so today we will try to see how we formulate this proof. So as I guess you have already noted in the classes that have happened in the last um, 1 week or maybe 2 weeks, that any greedy algorithm needs an optimality proof, and this is what we are doing for the Prim's algorithm now. So let us suppose that GVE was my original graph, and we define something. Let's say if be a subset of E, okay, and is termed as promising subset. Now, what is a promising subset? So a promising subset is a one if edges could be added to this subset to form a minimum spanning tree. Okay. So if you can add edges to this subset to form a minimum spanning tree, then such a subset is called a promising subset. Okay. Now, if you recall the example figure that we were working on, here V1, V2 and V1, V3. So this subset V1, V2, comma V1, V3, this subset is a promising subset. Whereas V2, V4 is not a promising subset. This is since V1, V2 and V1, V3 can be added to the set. Okay, so actually these are okay, this actually forms a set which is kind of a subset of the final spanning tree edges that we are going to obtain. Okay, which is not true for the edge V2, V4. So that's why the subset V1, V2, V1, V3 is a promising subset. So this is how we define a promising subset. Okay. So now with this definition, we will try to prove a lemma.
Sir?
Yes.
Sir, in the previous example, we can have V2, V1, V1, V3 in a promising subset.
Yes, you can have V2, V1.
Yes, sir.
That's what we said. V1, V2 and V1, V3. That's what we said. V1, V2 and V1, V3 as a promising subset. You can also have V1, V2 and V2, V3 as a promising subset. But you cannot have all three of them because then it's no longer a tree.
Okay.
Is that what you are trying to say?
No, sir, I was saying V2, V1 and V1, V3.
That's the same thing. V1, V2 and V2, V1 are the same thing. This is an undirected graph.
Yes, sir.
Okay. So now we will, using this definition, we will now try to prove a lemma. Now what is the lemma? Let's say GV is the connected weighted graph that we have with us. Okay. Now let F be a promising subset. Okay. Let this be given to us. Okay. And let Y be the set of vertices that connect the edges inside F. Okay. So Y is only those set of vertices that connect the edges inside F. Okay. Now, if E, small e, is an edge of minimum weight that connects a vertex from Y to V minus Y, then F union E is promising. Okay. So we assume that F is a promising subset. We assume that Y is set of all the vertices that connect the edges inside F. Now let E be an edge of minimum weight that connects a vertex from Y to V minus Y. Then we have to prove that F union E is promising. So this is the lemma that we have to prove. Okay. Now to prove this, we will divide the proof into two parts, as you will see. Part 1. Now, since F is promising, we can assume that in future it is going to lead us to a minimum spanning tree. Let's call it F prime. Okay. So since F is promising, in future it should lead us to a minimum spanning tree, and let's call that F prime. Okay. And this would happen. This would happen through the union of some edges. Okay. Now, therefore, we know for sure that F is a subset of F prime, because F later on is going to lead into a minimum spanning tree F prime, right? MST edges. Now, the case of part 1. Let's say E is in F prime. Then what can you say?
Then we are done with the proof.
Huh?
Then the proof is done.
Say E is already in F prime. Then what can you say?
So the lemma holds true automatically.
Lemma will be true automatically, because then F union E will be subset of F prime. Okay. And thus F union E is promising. The tricky case is when E is not part of F prime. Here what to do? From all that we have learned so far, does something ring a bell?
There will be another edge of length E.
There will be another edge. Very good. There will be another edge. Go ahead.
Length same as E.
Can you be a little louder so that the whole class can hear?
There will be another edge whose length is same as the length of E.
Whose weight is same as
Weight of
E, and there is something else. These two edges have a relationship.
Part of F prime.
If both of them if both of them get included in F prime, what will happen?
Means they connect to the same vertex.
Yes, that means they together form a dash.
Cycle.
They together form a cycle, like that example that we saw there. V1, V2 and V3, right? So any one of them should have inclusion permission in F prime. So if E is not in F prime, then there is some other edge E prime in F prime that is of the same weight as E, right?
Yes, sir.
Now we can remove that E prime and add E. This will still keep the F prime as minimum spanning tree. Sorry, the graph that we get, the tree that we get will still be a minimum spanning tree. Will it or not? Let's go back to this example and see. I'll give you a more concrete example. Suppose I remove this edge and include this edge, or I remove this edge and include this edge. Still it is going to remain a minimum spanning tree, right? So any one of this can be included. So if E is not there, E prime will be there. If E prime is not there, E will be there. Okay, and therefore the second part of the lemma also gets proved. So we'll write formally what is happening. So let's say E is not part of the edge set F prime. Okay, Now, since VF prime is a MST, F prime union E, what will this lead to? A cycle, right? A simple cycle. And E should be part of this cycle. We can illustrate it using a picture. So this is how the structure would typically look. Okay. So in this case, the cycle is V1, V2, V4, V3. Okay. Once you add E to the set F prime, right? Now, if we remove E prime from this set F prime, then again it becomes a tree as the cycle disappears. Okay. Also, since E is the minimum edge weight, edge connecting Y and V minus Y. So weight of E should be exactly equal to weight of E prime. Therefore, given all this, we can say F prime union E minus E prime is a edge set is an edge set of an MST. Okay. So then F union E should be a subset of anything else to be said? Why can we say this?
Because F is subset of F prime.
F is subset of F prime. But suppose E prime is already in F. Can that happen?
No, sir. E prime is an edge from
No,
y
sir.
to p minus y.
So E prime, this is true because remember when you are doing a proof, these small things need to be taken care of, because E prime cannot be in F since E prime connects nodes from y to v minus y only. Hence, it's promising.
Sir, I didn't get why E prime should not belong to F.
You tell me why E prime should not belong to F.
Sir, F connects the edges. But if in the example which you showed now, if V3 already belongs to V1, V3 already belongs to F.
You see what is y and v minus y here?
No, sir. After some steps, if V1, V2, V3 belongs to Y and V4, V5 is V minus Y. In that case,
So at that time you have included you have constructed the whole MST. There is no promising set anymore. So whatever is the case, at this particular situation, in this particular situation, E prime and E are exactly similar candidates in this stage of the construction. Right or wrong?
yes, sir.
And therefore, if E connects y to v minus y, then E prime also connects y to v minus y at this stage. So F, remember, F is a promising subset. It's not the whole MST. So we are backtracking. While in the stage of construction of F, at some point in time, if E was not in that set, then E prime cannot be also in that set. Right? So at that time, E prime cannot be also in that set. F is only consisting of nodes F is only consisting of edges that connect the nodes in Y. So that's why I was telling you that there is a temporality in this. So now, once we are done with the lemma proof, we will construct our theorem. So Prim's algorithm produces MST always. So we will use an inductive method to prove it. Okay. So we will show that F is promising after the execution of each repeat step. So the induction hypothesis What is the induction hypothesis?
At the nth step, F is a
No, hypothesis. The base case. Sorry. Induction base. Induction base. What is the induction base?
Sir, F has only
Huh?
Sir, null set is a promising set.
Yes. Phi is promising. Okay. Phi is trivially promising. Now, induction hypothesis is that let at any state if constructed so far be promising. What is the induction step? We need to show that F union E is promising. What is E here in the algorithm? So the edge selected is the minimum weight edge that connects Y with V minus Y. Okay. So if union such an edge should be promising, from the lemma. Let's call it lemma 1. Okay, we have already called it lemma 1. Hence, proved.
sir, can you please scroll a bit up? Yes, sir. Okay, sir.
Okay. So now, as I told you last day, that we can have different forms of locally optimal strategy, and Prim's algorithm was one of them. So today we will look into the other one, and this one is based on an application of disjoint sets. Okay, so the idea here is that you start with one node in each disjoint set. Okay, now you sort the edges based on their weights. Connect disjoint sets taking edges from the sorted edge weights. Stop when all the sets are connected. Okay, so this is the rough idea of the Kruskal's algorithm. This is a reasonably easy algorithm to interpret if you have the basic idea of disjoint sets understood. So let's
Sir,
yes,
sir, can you please explain it once?
yes, I'll explain. I'll explain with example. Okay. So let's take an example and try to see what is the method in which this algorithm works. We will take our same sweet example. Okay, so we have the edges sorted. Tell me the sort sequence. V1, V2, then V2, V3, then V1, V3, then
Sir, V3, V5 will come first.
then V3, V5,
Sir, V3, V5 will come first
Yes.
after V1, V2.
okay, yes. V3, V5, V1, V3, V2, V3, then V4, V5, and then finally V2, V4. Right?
Sir, you missed V3,
V3,
V4.
V4.
Fine, okay. Now empty subsets. First, what do we join?
Sir, V1, V2.
V1, V2 merged. Next,
V3, V5
now
merge.
this. These two merged. Then this, right?
Yes, sir.
All sets have been merged. Stop. So somebody was asking me the algorithm. Is this clear to you now? We will write the pseudocode if it's clear to you.
Yes, sir. Clear.
Okay, fine. So now, once we have this, we can go ahead and write the pseudocode. For that, we will use our traditional well-known disjoint set data structures that you have already learned, I am assuming. We will need one index and we will need two set pointers. Okay. And we will need some additional functions. Initial n. Okay. This initializes n disjoint subsets indexed as 1 to n. P is find I, makes P point to the set containing index I. Merge PQ merges the two sets pointed to by P and Q respectively. Equal returns true if the sets pointed to by P and Q are equal. Now with this, we are ready to write down our algorithm. Done this. M is the number of edges.
Sir,
Hmm.
sir, initial and initializes sets, but will it return? If it does not return, how will we use them?
No, that's what. So initializes a set of pointers to sets. Okay. Initializes disjoint sets and disjoint sets.
Yes, sir, but do we need a 2D array to, I mean,
That is internal. You need to store it somehow. These initial nodes, and we will uh, find them. Okay, we will use the find function to find them
okay, sir.
using pointer references.
Sir, could you please scroll up a bit? Okay, sir. Thank you, sir.
Now looks fine, right? You are using the find function to map the sets, and then you check whether the two sets have already been merged. If not, you merge them and add the corresponding edge to F. Now, what is the complexity? Sorting of edge weights. How much will it take?
M log M.
If you use something like merge sort. Okay. Now each of those initial, find, etc. What will be the costs? What will be the cost of initial?
Log n. Means
Find,
knockout
etc.
size.
Huh?
Order n log star n.
Order.
N log star n.
These will be all each can be done in log m, and there are m passes at the in the worst case. So that will be m log m. Now it turns out that, or it seems like that this algorithm is kind of, the complexity is roughly free of the number of nodes. Is this claim true? It depends on the number of edges only, primarily. So overall, we can say everything boils down to m log m. So it is free from the number of nodes, the complexity. Is this a true statement?
Sir, since it is a spanning tree, which means sir, the number of edges and number of nodes are approximate.
Since it is a spanning tree, so
So number of edges and number of nodes. I mean, only
but
one is.
remember, you are building the spanning tree from a graph which has n nodes and m edges.
Sir, if
Sir, we can
many
claim
nodes
this
are
because
not
it is a
connected,
connected graph. So m and n will nearly
So can't you say that the
m
point
greater than equal
complexity?
to m.
No, many of you are talking together one by one, maybe.
Sir, this is a connected graph. So m will
Connected
be at
graph,
least
yes.
n minus 1.
Yes, it's a connected graph.
So m will be at least n minus 1 and m can be greater than n. So we can claim this.
Oh, is that so? Okay, let us think from the angle of this. I had already told you while discussing or while introducing adjacency matrix versus adjacency list. What happens when you have a sparse graph? What can you say for a sparse graph?
Number of edges are close to the
M
number of.
will be O of n.
And what about a dense graph?
M will be O of n square.
So for a dense graph, the overall complexity for Kruskal can go up to how much?
n square log n.
N square log n.
Right. So then for sparse graph, if you know that the graph is sparse, which among the two algorithms will you use, Prim or Kruskal?
Sir, Kruskal.
Kruskal. And for dense graph,
Prim's.
okay. So this is something that will not leave you at least till your Grand Viva Voce in the 4th year. This is a question that comes like repeatedly. You will tell the complexity, then they will take you back to the reason for the complexity and things like that. So keep this in mind at least till you graduate.
Sir,
Oh, yes.
sir, what is the boundary line of sparse and dense graph?
This is a very like difficult question. Like, so just a minute, second. This is something is happening with my. Okay, so like the boundary line is not clear, but you have an easy estimate, right? So you can count the edges. you can count the edges, and then you can like see whether the number of edges is like, so suppose you plot the number of edges as a function of n. Okay, and then this curve, like as it like how to situate it better, let me think. So basically these things only matter in asymptotic limits or thermodynamical limits. So the safest thing would be to check whether, like, if m could be expressed as a factor of n. As long as this is possible, you are good to go with the Kruskal's method. If it is no longer possible to express m as a factor of n, then it becomes, or it gets into the Prim's boundary. Another tricky way to check it is to see like whether the adjacency graph is almost full or not. If it is, then you should probably not go with the Kruskal's algorithm. Okay, now a homework.
Sir, m is a factor of n means you are saying m is less than n.
M is, like, I would say m is similar to n, or some factor, say 2, 3, some small factor. Small. There is no hard and fast way of finding out this. One way is to compute the density of the okay, so another thing you can do. So I think I told you this. So compute connection density. What is that? So it is the number of edges in the graph by total number of possible edges. Okay. Now, if this is close to 1, then what does this mean?
Dense
It's
graph.
dense, yeah.
It's very dense. Okay. But if it is, say, somewhere around 0.2 or even lesser, 0.1, things like this will give you an idea. So there is a threshold that you have to set. This is an engineering threshold. This is a parameter of the algorithm that you have to set. And like this would be kind of your tolerance limit. Okay. So you will say, like, say, for instance, any network which has an edge density, say, less than 0.3, you are going to call it, say, sparse. Of course, anything above 0.5 is going to be dense. Should be dense. Okay, so homework, this you will do yourself. This will also be a practice for you. It is very similar, very similar to the Prim's algorithm, but you should try it yourself. Prove that Kruskal's algo always results in an MST. It's very similar to the Prim's algorithm, but try it yourself. I am not going to do it unless you have shown enough proof of you yourself trying. Once I have got enough proof that you have tried, I'm going to give you the solution. But it's very similar. The approach is very similar to what we have adopted for the Prim's algorithm. Try to do it yourself. This is a good exercise. And tomorrow we will talk about the Dijkstra's algorithm, which is very similar in spirit to the Prim's algorithm. And also we will finish off with the knapsack problem.
Sir,
Sir, will this be in syllabus? Prim's and Kruskal's algorithm.
Come again.
So Prim's and Kruskal's, will they be in the test?